For decades, Pluto sat at the edge of human knowledge, visited once, briefly, by a single spacecraft. Scientists believed they understood its frozen surface, its thin atmosphere, its quiet isolation. Then, the James Webb Space Telescope turned its instruments toward the distant dwarf planet. What came back did not match the models. The images revealed features no existing theory had predicted. Astronomers are still working through what it means. Pluto was discovered in 1930 by a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona. He spent months comparing photographic plates of the night sky, looking for something that moved. When he found it, a faint, slow-moving dot among the stars, the world celebrated the discovery of a ninth planet. For the next 76 years, Pluto held that title. Then, in 2006, the International Astronomical Union reclassified it as a dwarf planet. The decision was scientific. Pluto shares its orbital neighborhood with thousands of other objects in the Kuiper Belt, a region of icy bodies stretching far beyond Neptune. It did not fit the strict definition of a planet, but reclassification did not make it less interesting. If anything, it made Pluto harder to ignore. The challenge was always distance. At its farthest point from the Sun, Pluto sits roughly 5.9 billion kilometers away. That is so far that sunlight takes more than 5 hours to reach it. From Earth, even the most powerful ground-based telescopes could only produce blurry, pixelated impressions of its surface. Scientists had to rely on indirect methods, measuring reflected light, tracking its moons, modeling its thin nitrogen atmosphere, to piece together what Pluto might actually look like. In July 2015, NASA's New Horizons spacecraft changed that. After a journey of nearly 9.5 years, it flew past Pluto at roughly 50,000 kilometers per hour, close enough to capture detailed images of its surface. What it revealed was unexpected. Pluto had towering mountains made of water ice. It had vast plains of nitrogen ice. It showed signs of geological processes that, for a world so small and so cold, scientists had not anticipated. But New Horizons had only one chance. It was moving too fast to slow down in orbit. It captured what it could in a matter of hours, and then it was gone. Large sections of Pluto's surface remained completely unimaged. The data raised more questions than it resolved. Astronomers knew they needed another instrument, one that could look longer, deeper, and in ways no flyby could offer. That instrument was the James Webb Space Telescope. Built to see the faint, the cold, and the chemically complex, Webb was designed for exactly this kind of target. When its observations of Pluto were announced, the planetary science community paid close attention. They expected Webb to fill in the gaps New Horizons had left behind. Instead, Webb's first images introduced something no mission had prepared them for. To understand why Webb's observations of Pluto matter so much, it helps to understand what makes this telescope different from anything that came before it. The James Webb Space Telescope does not see the universe the way human eyes do. It operates primarily in infrared light, a part of the electromagnetic spectrum that carries heat signatures and chemical information invisible to both the naked eye and to most earlier instruments, including the Hubble Space Telescope. Where Hubble sees visible light, Webb sees through dust, cold, and distance in ways that were previously impossible. Its primary mirror spans 6.5 meters across, nearly 3 times the width of Hubble's. A larger mirror collects more light, the way a wider bucket collects more rain. This gives Webb the ability to study objects that are extraordinarily faint, or extraordinarily far away. In some cases, both at once. Webb also sits in a carefully chosen position in space called Lagrange Point 2. roughly 1.5 million kilometers from Earth on the side away from the Sun. From this stable point, it is shielded from the Sun's heat and light by a 5-layer sun shield roughly the size of a tennis court. This keeps Webb's instruments cold enough to detect the faint infrared signals it was built to find. For a target like Pluto, 2 instruments are especially important. The near-infrared camera, known as NIRCam, captures detailed images in infrared wavelengths. The mid-infrared instrument, called MIRI, goes further, detecting the heat and chemical signatures of surfaces at extremely low temperatures. Together, they allow scientists to identify specific molecules frozen onto a distant surface with a precision that no previous telescope could match. This technique is called spectroscopy. When light reflects off a surface and travels to Webb's instruments, the telescope splits that light into its individual wavelengths, the way a prism splits sunlight into a rainbow. Each molecule absorbs and reflects light in a unique pattern. That pattern acts like a chemical fingerprint. By reading it, scientists can determine exactly what a surface is made of without ever physically touching it. For Pluto, researchers expected to confirm what New Horizons had suggested: nitrogen ice, methane ice, carbon monoxide, and traces of other compounds. Webb's resolution would simply sharpen that picture. The instruments locked onto Pluto. The data began arriving at mission control. Scientists settled in to read the results. When the first spectral data came through, one of the signals did not match any known compound on Pluto's surface, or anywhere else in the outer solar system. The first thing scientists noticed was the heat, not warmth in any familiar sense. Pluto's surface sits at around minus 230 degrees Celsius, cold enough to freeze nitrogen solid. But Webb's infrared instruments do not need a place to be warm. They need it to be uneven. And Pluto's surface, it turned out, was uneven in ways no existing model had predicted. Webb's images revealed distinct thermal variations spread across different regions of the dwarf planet. Some areas were radiating slightly more energy than others, small differences, but measurable ones. And the pattern did not follow sunlight. On a world as distant as Pluto, solar energy is extraordinarily weak. The Sun, seen from Pluto, is little more than a bright star. It does not have the strength to warm one region of a surface differently from another. Whatever was causing these temperature differences had to be coming from somewhere else. The variations were especially notable near Tombaugh Regio, the large, heart-shaped plain of nitrogen ice that became one of New Horizons' most iconic images. Researchers had assumed this region was geologically quiet, a stable sheet of frozen nitrogen slowly cycling through Pluto's atmosphere over long periods of time. Webb's data suggested the picture was more complicated than that. Then came the chemistry. Webb's spectroscopy revealed complex organic molecules distributed across Pluto's surface in concentrations that did not match the models. Among them were signatures consistent with tholins, reddish-brown compounds that form when nitrogen and methane are exposed to radiation over long periods of time. Tholins had been detected on Pluto before. What was unexpected was where they were showing up. Under current models of Pluto's geological activity, the regions with the highest tholin concentration should have been among the least chemically active on the entire surface. The compounds were appearing in the wrong places. That kind of mismatch in planetary science is rarely a coincidence. Webb also detected something subtler. The density of Pluto's thin nitrogen atmosphere appeared to have shifted slightly compared to measurements taken during the New Horizons flyby in 2015. The change was faint, but it was consistent across multiple readings. Pluto's atmosphere, researchers noted, seemed to be responding to something. A world that scientists had long considered frozen and static was showing quiet but persistent signs of change. Teams began working through the possible explanations. Several emerged. Most were familiar ideas applied to unfamiliar data. But one kept surfacing in the discussion, and the more researchers examined it, the more seriously they took it. One explanation kept emerging in the discussion, and if it proved correct, it would fundamentally change how scientists understand geological activity in the outer solar system. The hypothesis that kept returning to the surface of every discussion was one that some researchers had quietly entertained since 2015. Pluto, they suggested, may not be entirely frozen through. Somewhere beneath its thick shell of ice, there may be liquid water. And based on what Webb was now showing, that liquid layer may still be active today. The idea was not invented in response to Webb's data. After New Horizons flew past, several research teams noted that Pluto's surface features were difficult to explain for a world with no internal energy. The towering mountain ranges, built from water ice, required geological forces to lift them. The smooth, unbroken flatness of Tombaugh Regio suggested the surface had been reshaped relatively recently. Not billions of years ago when the solar system was still forming, but on a timescale that implied ongoing movement. Something inside Pluto appeared to be doing work. Webb's observations gave that suspicion new and measurable support. The mechanism researchers are examining is radioactive decay. Deep within Pluto's rocky core, unstable elements, uranium, thorium, and potassium, break down slowly over billions of years, releasing heat as they do. On Earth, this same process contributes to the planet's internal warmth. On moons like Europa and Enceladus, a different energy source drives subsurface oceans. The gravitational pull of nearby giant planets creates tidal forces that flex and heat the moon's interior. Pluto has no such large neighbor, but radioactive decay requires no neighbor. It is a quiet, persistent process, and on a body as old as Pluto, it may have generated enough heat to keep a thin layer of water liquid far beneath the surface. The thermal anomalies Webb detected, those localized regions of slightly elevated energy, could be consistent with areas where that deep heat is slowly escaping upward through the ice. Not dramatically, not in the way a volcano releases heat, but in a gradual, steady seepage that Webb's instruments were sensitive enough to detect. Scientists are careful about what they say next. The presence of liquid water beneath Pluto's surface, combined with the organic chemistry Webb has detected and a persistent heat source, represents a specific combination of conditions. It is the same combination that scientists consider a minimum requirement for habitability, for the possibility, however remote, that chemistry of a more complex kind could take hold. Researchers are not claiming life exists on Pluto. They are noting, precisely and deliberately, that the conditions Webb appears to be measuring are ones that warrant serious attention. Teams are already drawing up strategies for follow-up observations, longer integration times, different spectral ranges. One group has framed the question in a way that quietly shifted how others in the field were thinking about the discovery. If Pluto can sustain internal heat at this distance from the Sun, researchers realized they needed to reconsider an entire category of objects in the outer solar system and beyond it. Pluto is not alone out there. Beyond Neptune, in a vast and poorly mapped region of the solar system called the Kuiper Belt, hundreds of thousands of icy objects orbit the Sun in slow, distant paths. Most are small, but some are not. Eris, Makemake, Sedna, these are worlds in their own right, large enough to be round, cold enough to be ancient, and until recently assumed to be completely inert. Frozen through, geologically silent. That assumption is now being questioned. If Pluto, one of the largest and best studied Kuiper Belt objects, is showing signs of internal heat and possible subsurface liquid water, Then the question has to be asked, are the others doing the same thing? Radioactive decay does not care which body it is happening inside. It is a function of mass, composition, and time. Any object large enough and old enough may be generating quiet heat in its core, regardless of how far it sits from the sun. Webb is already looking. Observations of Eris, Makemake, and Sedna are underway or in early processing. Researchers are applying the same spectroscopic analysis used on Pluto, searching for thermal irregularities and unexpected chemical distributions. The results are not yet complete, but the fact that scientists are looking, and looking seriously, reflects how much Webb's Pluto data has shifted the conversation. For decades, planetary science has operated around a concept sometimes called the habitable edge, an informal boundary beyond which conditions were considered too cold for liquid water to survive. The assumption was that without proximity to a star, or without the tidal forces generated by a massive neighbor, a world simply could not hold on to warmth long enough to matter. Webb's findings suggest that boundary is less fixed than it appeared. Radioactive decay is universal. It operates in every solar system, around every star, inside every rocky or icy body with the right elemental composition. If it can sustain a liquid layer inside Pluto, it may be doing the same inside frozen worlds orbiting distant suns, worlds that no current telescope could detect life on, but that future instruments might one day study more closely. The original question Webb set out to answer, what exactly is driving the thermal patterns on Pluto's surface, remains open. Scientists are still working through the data, but the search for that answer has already redirected the way researchers think about cold, dark, distant worlds. That shift, in itself, is a significant result. Webb has only completed its initial observations of Pluto. A second, deeper imaging sequence is already scheduled, and scientists are not certain what it will show. Pluto spent decades at the edge of what science could see. Webb has brought it back into focus, and what it revealed has opened far more questions than it closed. If this kind of discovery is what you come here for, consider subscribing so you don't miss what comes next. And if you have thoughts on what Webb might find in that second imaging sequence, or which Kuiper Belt object you'd most want it to look at, share them in the comments below.